Okay, hi again everybody. This is the second video. In the previous video I explained how what are the main parts of the programming and how we can connect our development board to the Atmega 8 on the breadboard. After seeing that, you should know what are the main parts of the program as a program in the CodeVision. Now we will start to reach to the. We are going to do 6 tasks that we have, and the 6 tasks you can see here. We should have a write a program to blink LED of frequency of 0.5 Hertz. By pressing and holding a push button, LED turns on, and by releasing it, push button off. So all of these codes, these tasks, 6 different tasks we will do, and through these 6 tasks we will get to know some tricks and some kind of techniques for controlling the input and output using the C programming functions. And also the most important part, we are going to use CodeVision Wizard for creating code. I will explain what the CodeVision Wizard is. So let's start with that. Here, this is the icon for the CodeVision. Let's click on it, and when it's running, then it will ask you to give a name for this is the old project. I don't want this. Let's go to top here, file, new project you can make, or you can make from here also new project. And you're about to create a new project. Do you want to use the CodeVision Wizard? Yes, I want. And it will give me this window. Here you have an option to choose the type of the microcontroller that you have. This one is, I'm using the Atmega type. So this is correct. I would say okay. And then it will ask me to name a first address. Where should I'm bringing from the laptop. It pops up in the laptop. That's why I'm bringing those. So this is the wizard. It closed. This is the wizard. Why it's happening? This window is the wizard for setting up our input, output. We don't have to do it in our code. We can set up everything here. All these tools that our chip has, they are here. You can see there's Atmega32A is here. First we have to, let me open this. I feel we need that in the back. Well, okay. The old program, we don't do anything. Here, the most important that we are selecting is the chip type. That for us here is Atmega 8. Be careful. Here it says what is the frequency that it has to work, the system clock. You can select different types, but 8 megahertz is what we will use. It can be from low 1 to 16 megahertz, or maybe even lower than 1 if you are using external clocks. But 8 megahertz internal, what we plan to use. So this is chip that we just selected. Here program type is application, and we don't need the other types, bootloader and those, we don't deal with them, just application. The second part after the chips is the ports. Here you can see Atmega 8 has 3 different ports. We want to connect, as you remember, we connected, let's see here, you see the push buttons S1 and S2 are connected to the pin B0 and pin B1, and they should be input and pulled up, internally pulled up. And the pin C5 is connected to the LED. All the other pins, the wires for the programmer, they should always be there. So let's go here. So we say port B0. If I make it output, it will like turn the output, you see. I say that they are input, but not tri-state. All of them are in tri-state right now. And I click here, pull up. So these are right now input, pulled up. P means pulled up. Pull up output. Yeah, you can see up here also. Data direction, input or output, pull up output value. The second part is that we want the port C pin 5. Which one should be the port C? 0, 1, 2, 3. So this is correct. Port C5 to be output, this one, and the value should be 0. Pull up. When it's output, it just turns on and off. It's not pulled up. So we have output. The pin C5 would be output, and its value initially is 1. If I make it initially is 0. If I make it 1, it means that the LED will be on as soon as I start the microcontroller. But now I make it 0 so that the value is 0. It's turned off. Port D we are not using, so we don't change anything here. The other tools that or Atmega 8, the chip. You see here I have the Atmega 8 chip. If I choose another microchip, the CodeVision AVR wizard will give me different tools. Because it has a library, it knows what chip has what kind of tools with it, what kind of timers, what kind of abilities it has. So every chip that you are selecting at the beginning, the CodeVision AVR changes this menu for you according to the type of the chip that you have. Now we have Atmega 8. These are the tools that this microcontroller has. It has 3 ports. If you select, for example, Atmega 32A, it has 4 ports, port A, B, C. This one has only 3. Then external interrupts. Interrupts, if we want to use interrupts, we can activate any of them that we want here. If we activate based on this click that if I make here, it will, you see all of these are options that later in the projects we will use all of them. If I click here, for example, in the configuration part of the code, the wizard will write all of the necessary like code that is needed to use the interrupt. So we don't have to go there and write all of the inputs and outputs and set the bits one by one. So you will see later, right very soon, you will see how many bits need to be configured in order to use different tools of the microcontroller. So right now I'm not activating the interrupts. The next thing is like timer and counter. The timers, as you can see, this one, Atmega 8 has 4 different timers. One is timer 0, which is in the mic. The timers can be 8-bit or 10-bit. And in the datasheet, you can see all of those information. And every timer has different characteristics. So depends on which one of them I activate, it will be the code configuration part of my code will be different. Watch dark timer also is something that in some projects we need to use. UseArt. What is UseArt? Is the communication protocol that we have learned about. If you have the UseArt here in the menu, it means that our microcontroller has the ability to do communication through the UseArt. If this is and you can activate only the microcontroller to send information, or for example, you have two microcontrollers, one can send and the other can receive, or both of them can be sender or receiver. Based on this, our configuration will be different. Right now we don't need any of them for blinking tasks, so we don't turn them on. Analog comparators. We can use the microcontroller. Some pins, we have special pins that if we activate here, the comparator tool will be activated. So we can have signals in those two pins, and the microcontroller can compare those, and based on that can run some logic. Like analog to digital converter, you know what it is. If we have a signal that comes from analog signal from a sensor, we want to turn it to the digital, we will activate this analog to digital serial SPI interface. If we want to use the SPI communication, we should activate this one. 2-wire or I2C interface. If we want to communicate, we have to activate this one. Bitbang, the I2C bus interface. This is another type of interface that I2C is this one, TW. So these are a bit different, and we have to activate them when we want to use them. Then one wire bus interface we can have activated, then bitbanked peripheral. I've not used this one, so and in our project we will not need, but if you are interested you can study more about them. We will use TWI, 2-wire interface, and the UseArt. Alphabetic LCD, if that we will work with it also. If we are planning to connect the LCD to our programmer, we can enable it, and according to that, a menu will open here for us to connect. Right now we didn't change anything, we didn't enable anything, just the ports. So here in the ports, as you remember, the bit 5, I turned it to the output and the value 0. Port B, bit 0 and 1 as an input and the pull up. And when this is done, we will make a program, generate, save, and exit. When I press that, it will ask me where to save it. Let me decide where can I, in the desktop I will create like with this icon, I create first, what to name, at 8 test. I made a folder, and then I select it, and for the name I put at 8 test. I copy this because I have to give, here it says this is the name for the .c file. I save it, then it will ask again for the .prg file. I paste the same. You can give them differently, but it's okay if you are giving all of the same. I'm giving all of the names same. And here is for the .cwp file. There's different files for the project, and After you click OK, see what it made for us. This is the raw file. In the beginning explains when this is made, who made, and what type of chip it is, in what frequency is the system, clock frequency, normal, memory model, small, external, RAM size is 0, we don't have any external. Data stack size is 256, okay. So, as you can see, it has added the type of the chip as we expected, and now we want to write the program so that it will. Okay, let me explain the rest before. Let me add the Control-C, the delay. For sure, we will need the delay. Delay is needed in our program. Declare your global variables here. We will come to here. Void. This is our main function, and you see all of this code is the configuration part of the program that the wizard made for us. We don't need to do anything. This is just the base, like empty form that if we want to use, we have to change some data, but it's giving value for different registers. All of them have some default values. These are just giving value to different functions like timer, counter. Let me say from the beginning. Explanation about the project, what it is, what it does. Then the libraries that are added. Here we will add the variables that we will need in. Declare your local variables here. If I have a local variable that are valid only in the main function, I have to declare them here. If you declare your variable, global variables are up here. Input, the local and global, the difference is that if you are like putting a variable here, it will not be recognized outside of the main function. But if it's a global, it will be recognized everywhere in the function. Then input output port initialization. This is like telling to the microcontroller what type of the like the data direction for all of the ports. We have a port B, C, and D. So this is for the port B. You can see there is 8 bits. Bit 0 should be 0. Bit 1 should be 0. Bit 2 should be 0. Bit 3 should be 0. Data. So all of the pins of the B are input. But we had only one output. Let's go find where it has been set up. The bits 0 and 1 are set to be pulled up, as you can see. Bit 0, port B0 has become 1. Port B1 has become 1 also. This is the pull-up ones that we made. This means that we made those bits input and we decided that they should be pulled up. That is implemented here. All those selections that we had, it comes here. Oh, then all other pins are 0, you see. All other pins, pin 3, 4, 5, port B, pin 3, 4, 5, 6, all of them are 0. It means they are in the try state. They are not pulled up like this one. Then port C initialization. Here we had made a port C.5 as output, and that's only one that is here that has made output. All the others are like in the try state, in the 0. They are not output. They are in the try state or input, you can say. Okay, then for the value of the port C5, we have given 0. We don't want the LED to turn on, so we have it 0. Then port D, we haven't changed anything, so by default, all of these numbers are set to be 0. Data direction to be 0 for all the bits, and the value of the pull up also all is 0. None of them is pulled up. If we use timer counter initialization, this part of the code is for initialization of the timer. You see, these are the register numbers that in the data sheet you can see what is the timer counter value, the start value or comparison value that is right now 0 is given. It means the timer is initialized, but we are not using it. We are not adding anything here. Timer counter 1 initialization, clock source, all of the information about the timer we are not dealing with. This was timer 0, timer 1. These are the registers addresses for the timer 1. We have a timer 2. All the registers related to the timer 2 are here. Their value is given. Then timers, timer interrupts are used with these registers to be like configured. Then internal interrupts, if we wanted to like have here right now in this setting, it means internal 0 is off, internal 1 is off also. So the comments explain what each register does, what is the configured situation. UseArt initialization, UseArt disabled. Yeah, we didn't activate it. So all of these register values are set in a way that the UseArt communication is not active. Analog comparator initialization, as you can guess, the registers are regarded to this. In the datasheet, you can read in detail what these registers are, what each bit mean, because every bit here changing will change the behavior of the microcontroller. Analog to digital initialization, disabled. With this configuration of this register, this is disabled. If we enable, this configuration will change to some other way. SPI disabled. This is serial peripheral interface. This code is for that. TWI initialization, two-wire interface is disabled. And now we reach to our code here. The little while loop that we have is the code that will run forever. The rest of this code that is inside the main function, the CPU will read them and execute them only once until it comes and reach here. All the configuration is read, it memorizes, and then comes here and does this piece of code that is inside the while loop and stays here forever, like basically until you haven't turned off the microcontroller. Microcontroller will be doing this cycle here, and that's all for this. So now let's go to our task and start to solve our tasks. Here is our task. Now I will go, because I have actually the solution for this in my screen so that I don't have to type. As you know, I hate typing with different keyboards in different laptops. Each of them is changing, and I never remember where to find which character. So I have already typed the code. What I need to initialize, like Control C. Here in the declaration of the variables, I will declare an integer I, which I will use in the code. And I will see I'm not using anything else. So let's go to the while loop. All of those, only one variable is added there. I go to the while loop and start in the while loop. The first piece of code will be transfer to the blink one. Control C. Yes, this is the first code. You can see what it will do. Answer to the first one is this that. First, when the program is running, it will turn on the port C value on, give the high value to it, delay 1000 milliseconds, and turn it off. This is the answer to the part 1 of our task. By pressing this, write the program to blink LED frequency of 0.5 Hz. 0.5 Hz means that in the period of this, in every second, it has to complete half of its period. So the period should be 2 seconds, so that half of it is 1 second. 1 second it turns on, the other 1 second turns off. So we give 1000 millisecond delay for it and for on and off was. And the second is that by pressing and holding the push button, LED turns on, and by releasing the push button, LED turns off. This is quite simple. You know what I will put here to deactivate the continue. I put a continue, and it means that this code will not be even read anymore. Anytime the program comes here, reaches to this continue, sees it, then it goes to the beginning of the cycle. So I have to write the task, the answer to the second task here. Let's do that. Control C and Control V. I make it a bit nicer. Let's put some indentation a bit here so you can see what is here belonging to the if condition. This is part of the if condition. Oh, it could be actually here. Yeah. So I make a space here. And so we say if the pin B is pressed, port C on, else if it's not pressed, port C is off. That's simple. And let me see, what is this pin? C equal not pin. Oh, this is how you can be also, you can write also. There's actually two ways to write this. One is this pin C. This is more similar to what we think, but when you are a little more experienced with the programming, you will know that it's possible to make it pretty short. You don't need to write if condition even. You can just write, I want port C to be the opposite of, this is the not the value of the pin B dot 0. Pin B dot 0 is our like the input pin which our push button is connected to. Pin register, this pin B dot 0 says goes and reads what is the value that is there right now. It is 0 or 5. So if it is 5, it means the push button is not registered, is not pressed. This not makes it like what? Let's say if it's not pressed, here we have 1, not 1 is 0, so port C.5 will be 0. If it pressed, here will be port pin B0 will be connected to the 0, so it's 0. Not 0 means 1. So port C.5 will be on. So this tiny piece of code does the work of these 4 lines. Right now I make the 4 lines back and this one as a comment, so later you can test it. So this was the second task. Let's go to this one, the third one. By once pressing the push button, LED turns on, and by next press, LED turns off. Toggle LED by each press, basically. So let's get here, and I will copy and paste the continue here because I want to separate this answer to the second question from the third. Anytime the code, the program pointer reaches here, from here goes back to the beginning of this next cycle. It ignores this. It will never reach here if I have a continue here. And so here I have to write the third code. And I have it ready here, so I will just copy and paste. So this is the third answer to the third part of the code. There is some issue here that it is part of that, yes. Oh, here is some important facts that let's look over them. This we don't want. So answer to the third part, what was it supposed to do? By once pressing the push button, LED turns on, and by the next press, it turns off, toggling. Here we say while pin, this is very interesting command that you see there is no, there's just condition. And there is no command. It's not like this while loop that while a condition and there's like curly bracket to include some code to do. If we don't have the curly bracket, or if we have it just empty, no, again I have this problem. If we don't have the curly brackets and we have the semicolons, it means this is the full command. And we basically say to the microcontroller that if this is 1, stay here. We don't say anything else to it. If this is 1, don't do anything, just stay here. it means while pin B equals 1, it is pulled up. You remember, it's not, it means if it is equals 1, it means it's not pressed. And so we say to the microcontroller, until the push button, this pin B0 is not pressed, the push button is not pressed, stay here, don't go forward. So the program pointer comes here, reads this, and sees this. Yeah, it's not pressed, so I stay here. I will not go forward anymore. When you press the push button, this is not true anymore. When you press the push button, the pin B0 will be connected to the ground, so the value will be 0, and this condition is not true. So program pointer passes this line and goes to the next line and turns this port C dot 5 equals not port C dot 5. Like, this is a simple technique for toggling value. Like, if it was 1, not 1 is 0. If it was 0, not 0 is 1. So this code just toggles it. Then we are coming to the next line. Why do we have this one? This is because when you are pressing, please pay attention in here, it toggled it. But how long do you think how long this process takes, the toggle? In this code that we have, like we have 600, a few hundred lines of code, it will take like maybe 1 millisecond. No, not like 100 millisecond or 100 microsecond or something, like 200 microsecond for entire this code to run through. And so the microcontroller does this 1 million times a second. If we have 8 megahertz clock speed that we have in this project, is like 8 million times a second it's reading this code. It's just repeating this cycle over and over again. We have only 4 commands here that are in every second. They are done like 8 million times divided by 4, like let's say by 10, by 8, 1 million times they are being done. So 1 microsecond, if you keep your finger here, you press the button, it reads it basically hundreds of times, and hundreds of times it toggles it. In order to solve this problem, we tell that after you toggle it here, wait while the button is pressed. So here was wait while the button is not pressed. You pressed it, then it has to wait again until you release it. And then this delay is added for in order to skip the bouncing effect, the bouncing effect that is in the push button. Because in the push button you might have a bouncing effect, and when you are pressing the like a push button, like maybe hundreds of signals up and down, 0 and 1s come to the microcontroller. But if and all of the process of the bouncing signals will be only less than 5 milliseconds. But so if we have 50 millisecond delay here, we are sure that those debouncing, those bouncing effects have passed, and here the program again continues to the next cycle. Another thing that I need to explain here, that human cannot press the push button like less than maybe I don't know, 30, 40, 50 milliseconds. So you cannot just press the push button. We will maybe you are pressing it like 50 millisecond, maybe 100 to 300 millisecond. If you are pressing, you try to do as fast as you can. It will be still like 100 milliseconds. So when you are pressing this microcontroller in the 100 millisecond might do this while loop maybe a million times. So in this, if you are not using this while loop, you will get always a random output. It might be on, depends on the value that is odd, or even the signal that is gotten, it will be on or off. But if you are putting this code here, it will wait until you're pressing the push button. If you are, then it goes toggles the LED. Then it waits until you take off your finger. Then here it waits 50 milliseconds here, ignores all of the bouncing signals that are coming because it is counting its pulses. 50 milliseconds is enough for all of the pulses from the noise of the bouncing noises to disappear. Then it goes to the next cycle. So this is basically one of the most important ones that I hope you can think about it and analyze it and understand why we have the delay here, how this works, how while works. We have two loops waiting for the button. Okay, that is the third. That's the third. What was this? Let's go to, I'm copying and pasting the fourth one also here. So we go to the fourth answer. This was third. Fourth. Again, there's this continue so that the rest of the codes will be ignored. I will check the... so where was that? Not this. Yeah, the fourth one. By once pressing the push button, LED turns on for 5 seconds. So every time we press the push button, LED has to be turned on for 5 seconds and then turn off. After 5 seconds, it needs to turn off. Here, it's just simply we write while pin B is 0 wait until while pin B point 0 is not pressed, it is pulled up, is 1. Wait here. If it is pressed, then you pass from here and then turn on the port C, make a delay 5 seconds and then turn it off automatically, and then returns to the beginning of the cycle and stays. You will do this on the microchip, and every time that you do any of them, you have to press this. For example, in the other video, my picture was in this corner, so you could not see what I'm doing, how I built the project. For example, here, I wrote this task. I would go here, project, and build all. After I press that, this kind of window comes here to me, and it has given me a warning. 0 error, should be 0. Yeah, no error, just one warning. Here also you can see no error, one warning. The one warning is that I was declared but not referred during the program. It's not used. I know that's we have not used it before. So every time that you have like done this code, you just need to go to this menu, project, build all, and then your hex file will be created. Then you have to go to the ProGISP. I will go on it later. Right now the chip is not near me. Atmega 8 is not near me, so I will show how how you can upload the file into the microchip using the ProGISP software. After this video, I will show in another separate video. So this one is done. This was the fourth part. The 5 will be LED switch is on by first push button and switch is off by second push. So this is very simple. You just need to use two different push buttons, pin B0 and pin B1. Okay, let's see the code for that. I have already here. I just need to copy and paste that. Right. I have this ready, but I hope you can write it yourself. You don't do copy and paste. Oh, maybe I don't share this code with you because you will do copy and paste. You better write it. Oh, good idea. Sorry, but yeah, I will not share this file with you. You see in the video, you can have a screenshot, but you cannot make copy and paste. That skips the possibility for... Yeah, this is code for the fifth task. You just write, if pin B.0 is pressed, port C should be 1. If pin B.1 is pressed, port C 0.5 would be 0. Nothing else. Here you don't need any delay, anything else, because for example, you pressed it, then it comes and turns it on. And the other pin is not changing. They are not connected together. So one pin, the other pin, and two different push buttons. Based on them, you turn on and off one output. Let's go to the next one and the last one. I don't want to make long videos, so you can find everything there. And the sixth task, I will just copy and paste again. So the sixth task will be this. Here is twice used if condition is inside another if condition. Indentations can help you to understand this. Okay. Actually, this can also, yeah. So this way it would be the continue also the same function. It just breaks the loop, like ends the loop here and then goes to the beginning of ends the cycle and goes to the beginning of the loop. So here, let's see what the task was. 6. By pressing and holding first push button for 4 seconds, the LED turns on, and by pressing the second push button, instantly LED turns off. So here's 4 seconds. It's a bit tricky and it needs more syncing here. If we press the push button less than 4 seconds, the LED should not turn on. This is a conceptual task, so that you try to understand how this logically program is working. In here, we say that if pin B.0 is 0, it means it's pressed. The push button is pressed. Then we make a delay 3,000. It can be 4,000 basically. 4 seconds. 4,000. Then if pin B is pressed, then do this port C. Like this is basically like that. This code has problem. It's not working properly. Guess how it's not working properly. If pin B.0 equals 0, then delay 4 seconds. After the delay, come and check if the pin B is still pressed, then turn the port 5 on, delay 500 milliseconds, and then turn the port 5 off. Think of what is the problem here. This one is, it might work, but imagine if this is 4 second delay. You press the pin B0 for 1 second, then release it for 2 seconds, and then press it again. In the middle, for 2 seconds, you release the pin B and the push button, and then press it again. This program was counting its pulses to be for milliseconds. It was not here. It was in the delay function. In the delay library, it was counting its pulses, like how many millions of pulses until 4,000 millisecond time is passed. So the program pointer was somewhere else. You release the pin B for 2 seconds, and then you pushed it again. It came and checked after 4 seconds. It's pressed still or not. It didn't monitor this push button during the 4 seconds. During the 4 seconds, it went somewhere else and it was counting the pulses. But this is not how our task is. Our task is to see if we press the push button less than 4 seconds, the LED should not turn on. This is a key part of the question that now you should think of a solution for this, how you can do that. So I don't give the answer to this. I let you analyze, think about it, like digest it to get the understanding how the process of the executing the program works. And when we have done it, as you see, I solved this. I will put it like program. Let's put it, I would make a build all. And when I did the build all, it still gives me the error that the I is not used, but it doesn't. If it's not error, it's warning. Warnings are okay. Warnings are giving you valuable information so that you can optimize your code. Sometimes warnings can give you some information that is actually necessary. You need to take care of it before your program can work. But right now, I know that this integer I is defined, and I have not used it. It doesn't matter right now. So I built my project. Let me show where you can find the project. So let's see. I go to the desktop. In the desktop, you remember the name. It was this @8 test debug. Let me see what other codes. You see all of the different type of the code project, CWP, all of them are here. Inside the debug, inside the exe, this is the code that, let me put it, I copy and paste. Control C, Control V. It came to my desktop. I have to just find it. It is in the iPad. no, in the laptop. So this is the, you see .hex, the name that I put .hex. This is the file that I have to download to my programmer, download to my, what is this? To my, not programmer, to the MCU microcontroller. And for this, we are here. Let me, okay, I will show in the next video. Let this be finishing the video because it's too long. Then the next part I have to explain about the fuse bits and everything. So let's close this here, and then I'll go to the next project, so that's next video, so that I can explain all about the fuse bits. Okay, thanks, bye.